Okay, let's study arc length. Here's the deal. Picture this as a road, and we have some starting point x equals a, some ending point x equals b. If we were to travel along the road, how far would we have traveled? We're in search of the arc length, the distance traveled along the curve from some starting point at x equals a to some ending point at x equals b. And so, as we typically do to derive formulas in calculus, we take the interval from a to b and we chop it into subintervals. And so here's an example subinterval, x sub k minus 1 and x sub k. Alright, and so we'll first chop it into 5 subintervals, we'll say. And these straight line paths can be an approximation. The sum of these straight line distances can be an approximation to the arc length. You can see it's a rather poor approximation, and the goal would be to have more subdivisions to get a better approximation, and eventually take the limit as the number of subdivisions goes to infinity. And so let's just take a look at one of these subintervals here, xk minus 1 to xk. There's 2 points here, and so my function is called f of x. So this particular point has the x coordinate as xk minus 1, and the y coordinate is f of that. The other point that's up here has coordinates xk and f of xk. So if we're to find the line, that the distance, how long the line is that connects those points, we'll just go back to pre-calc and look at the distance formula. And so distance formula will be made up of the difference in y's squared, difference in x's squared, using the Pythagorean theorem. And so we'll have the difference in x's squared plus the difference in y's squared. And then we take the square root. That's the distance for that particular line segment. Okay, we're going to do some algebraic manipulations to this in order to end up at the derivation, in order to work through the derivation and end up with our formula for arc length. The mean value theorem says basically that somewhere on the interval there'll be a place where the derivative has the same, the tangent line has the same slope as this is called a secant line. And there's a place, we'll mark it off as here maybe, a place where the tangent line has the same slope as the secant line. That's what the mean value theorem will say. And that symbol here means there exists some kind of xk star in our interval where it's true that the slope of the secant line, which is what's on the left-hand side here, is equal to the slope of the tangent line. At least one place. We're guaranteed that by the mean value theorem. The function is continuous and the function is differentiable. So we're guaranteed that. Now, here's what we're going to do with that. We're going to take this equation and manipulate it. Let's multiply both sides by xk minus the denominator, xk minus 1. So I have my y values subtracted will be equal to that derivative value times the difference in the x's. This is a different take on the mean value theorem. Some people actually write this as the mean value theorem, this version of it. Okay, so now let's go and replace the second set of parentheses here. Replace that with what's on the left-hand side here. So we have f prime of xk star, xk minus 1, quantity squared. Still squared. And the x difference is still here, and squared. Okay, now we're going to do some algebra with this. If we have a product, a times b, and it's squared, then we can square the a and square the b. We can distribute that, as long as it's multiplication. And so, we're going to call xk minus xk minus 1. We're going to call that delta x. And so here's what we're looking at. If you square the derivative and square this guy, and notice that it's also here, then what we can do is factor it out. Let me write it above here. We're going to factor out the xk minus 1 quantity squared. If we factor that out, we'll be left with 1 from the first term and f prime at xk star quantity squared. Just that f prime is squared, sorry. And then this is all underneath the square root, and so we have a perfect square here. Underneath the square root, it can come out, and that's why this is not underneath the square root. It's called delta x, the difference between them. So this is our distance for that one single piece. A different way of writing it. Alright? And what we're going to do is add up. In this case, we're looking at 5 such line segments. And so the arc length is going to be the sum of these line segment pieces. This represents that distance d. Sorry. This represents that distance d that we have from above. And we add up the different distances over a finite number n. And we see that to get more exact, we'd have to use more subdivisions. And so we want to take the limit, and it'll be a limit as the length of the subdivision, basically the length of the subinterval, goes to 0. So this delta x, which is the length of the subinterval, this difference in x, this delta x is going to go to 0. And so the distance of the length of our subinterval is going to be infinitesimally small. And this is a Riemann sum. The limit of a sum becomes the integral. And that's why our arc length formula will be the integral from a to b, that's your starting point and your ending point, of the integral of 1 plus f prime of x quantity squared, dx. And so that's the derivation as to why arc length has that formula. Okay, it's okay if you didn't follow it. I just want you to at least be able to see it. And now let's work it for 3 examples. We'll start from the easy example, then a medium, and then what I think to be a quite difficult example. First up, it would be what I call an easy example. I have this curve. I should draw a picture for you, but maybe I can pause the video and make a computer-generated picture of this. And so we have this curve, y equals 1 plus 2/3 times the quantity of x minus 1 to the 3/2 power. And we're going to take that from 1 to 4. We're going to walk along that curve from 1 to 4. When x is 1, we'll be at y equals 1, and when x is 4, we'll be at something like 1 plus 2/3 times 3 to the 3/2 for y. We want to work the formula. Remember, the formula has the derivative squared, and we add 1, and we take the square root. Derivative squared, add 1, take the square root. So, what is the derivative? Well, the derivative of 1 is 0. We bring down the 2/3, we have the 2/3, we bring down the 3/2. That cancels that out. We'll take x minus 1, take away 1 to the 1/2, and then there's no real, I guess if you want, the chain rule is multiplying by 1, the derivative of the inside here. So essentially these guys that cancel out, and we just get x minus 1 to the 1/2. That's the derivative, y prime. The formula has us squaring y prime. Well, conveniently, it's underneath a root. So we just get x minus 1. The formula has us adding 1 to that, and then taking the square root. So we have our x minus 1. We add 1 to it. Conveniently, those guys cancel out. And then we take a square root of the whole thing, and that would just be the square root of x. So it's very special how you can always, with this particular example, it's very special how we can end up with something that we can integrate. You'll find that not many functions can you end up with something at this point that you can actually integrate. And so they're very limited in the amount of examples you'll see for arc length questions, because in the end you want something that you can integrate, and at this point, from what the integration techniques that we know, we're kind of limited. And so this is what we're integrating from A to B, this A being 1 and B being 4. It's just root x, so it's x to the half. So it's x to the 3 halves. But instead of dividing by 3 halves, we'll multiply by 2/3. And then we plug a 4 and we plug a 1 in. Now 4 to the 3 halves, you can either do it like it's done here, where first you take it to the 1 half and then you cube it, because it's a perfect square, and it would be 2 cubed, which is 8. Another way that I like to do it is to just rewrite 4 as 2 squared, so that when you raise it to the 3 halves and you multiply these exponents, these guys cancel. You end up at the same place, 2 cubed, so you get 8. So this guy's an 8, and we take away 1 from it, that's a 7, and we take 2/3 of 7. This whole thing, this whole square bracket is a 7, 2/3 of 7, we get 14/3 as the arc length. Walking along that curve, from x equals 1 to x equals 4, along the curve, we get 14/3 as our arc length. Okay, consider that an easy one. And so we'll consider this next one a medium question. It looks the same. I mean, 2/3 is still there. Instead of it's still raised to the 3 halves. We're going from 0 to 3. This one's going from 1 to 4. The difference is what's inside. This one has 1 plus x squared, while the other one had x minus 1. The process is the same, though. We're to take the derivative. Okay. Now how do we get that? Well, the 2/3 is already there again. We bring down the 3 halves. We take 1 plus x squared to the 1 half. Chain rule comes in and we multiply by the derivative of the inside. And then once again, these guys cancel. So we're left with 2x times the quantity of 1 plus x squared to the half power. And that's what we need to square. So it's 2 terms multiplied by each other. This guy and that guy. We need to square them so we can square each one. Square the 2x, we get 4x squared. Square the 1 plus x squared to the half, and we get 1 plus x squared. Now, we want to add 1 to this. Let's go ahead and distribute this across. We're talking about 4x squared and 4x fourth. And we're going to add 1 to it. So we have 4x, and so 4x squared and 4x fourth. But we're going to write it in decreasing order like we like to see polynomials in. So that's why when we get to this point, sometimes it gets stuck, because the next step is to be able to integrate this, and it doesn't look like you can. And so what you have to search for is a way to be able to represent this guy as it is a perfect square. You just have to be able to see it. It factors. Okay, what you do is you treat it as, let's act like it's, I know it's 4x to the fourth, but let's let x squared equal w. Okay, it factors like 4w squared plus 4w plus 1. That guy factors to be 2w and 2w and 1 and 1 and plus and plus. And so our guy is going to factor as 2x squared plus 1 and 2x squared plus 1. Okay, and we can write that as 2x squared plus 1 quantity squared. So that's the algebra there. You would like to be able to represent what's underneath the square root as a perfect square, so these two operations undo each other. And when it comes time to integrate, then you're just integrating this polynomial term. 2x squared plus 1. It won't always be that, and so there's only certain instances where we could do that. Later we'll learn a technique that will help us be able to integrate roots called trig substitution, but for now, this is where we're at. And so we integrate 2x squared plus 1 from a to b. This time a is 0 and b is 3. So what made this one more difficult than the last one is that we needed to be able to recognize that this guy actually was a perfect square. We had to rely on our algebra to be able to recognize, yes, this guy is a perfect square, and to be able to factor it. Okay, so we get 2x cubed over 3 and x evaluated from 0 to 3. So we put a 3 in, and we get 2/3 of 27. Let's write that out. we get 2/3 of 3 cubed plus a 3. And then we put a 0 in, we get a 0. And so this 3 would cancel with one of these, still leaving you with 2 of them. So that's 2 times 9 plus a 3, or 18 plus a 3. And that's how we get this 21. Okay? Alright, great. So consider this the medium one in difficulty, and we save the worst for last. Here we have this function, 1/3 root x times the quantity of 3 minus x. And we're interested from 0 to 4. Okay. And the problem is, the way the function is given to you, maybe not the best way to get started with it. I mean, we want to be able to take its derivative, and as it is right now, it looks like we have to do a product rule. So we're going to distribute this guy across. Rewrite the function. Maybe the function should have been given to us like this, where the 3's would cancel, and we have root x. And then, when we distribute across the other guy, we'll have x times root x, which is x to the 3/2. It's x times x to the half. You add them up. X to the 1 times x to the half. You add them up. 1 plus a half. And that's how we get x to the 3/2. And then it's over 3, and there's a minus sign from that distribution there. And so we're going to deal with this guy instead. We're going to have to take the derivative here. Remember the formula, 1 plus y prime quantity squared, and take a square root and integrate from a to b on that. It doesn't have to always be an x. If the function is described for you, x is a function of y, then we can do it in y. But here we go. And so we need to take this derivative. What's the derivative of root x? If your function is root x, that's x to the half. And the derivative of x to the half is 1/2 x to the negative 1/2. And we're going to simplify that and call it 1/2 root x. How about the derivative of the second part? Well, you keep the third there, you bring down the 3/2, and then you take it to the 1/2. So we call this 1/3 times 3/2 times root x. So these 3's cancel. So here's what we're looking at. We're looking at 1/2 root x, this first term, and then minus root x over 2. That's our derivative. We have to square that. And so we need to multiply it out, it by itself. Okay. And so this is our derivative. We need to square it. How do you square it? Well, you multiply it by itself. Let's FOIL this out. Okay, what do we get? Well, what about the first? 1/2 root x times 1/2 root x is 1/4x. Okay, the outer. 1/2 root x times root x over 2. The root x is canceled. And you get negative 1/4. You get the same thing here. The root x is canceled, and you get 1/4, negative 1/4. And then finally this one, root x and root x is an x, 2 and 2 is a 4, so we get plus x over 4. And these guys combine to be a negative 1/2. Okay? Alright, great. So that is the derivative squared. What are we supposed to do with that? We're supposed to add 1 to it, and then take a square root. And so we put 1 plus it, and we have a square root. And this is the point I want you to focus in on. When we squared it out, the middle term was a negative 1/2 in this case. When I go and add 1 to it, and I can combine these now. I don't need this parentheses here. I just wanted to isolate it for you, but I can combine this. 1 minus a half is a positive half. So it has the same elements as that square had, except for the sign in the middle is now a plus when it used to be a minus. Emphasized by making the plus sign red. Okay, and like in the previous problem, it doesn't look like it at all. It's definitely much less recognizable than it was in the previous problem. This guy, yes, is a perfect square. And the way you're going to know what it is you're going to go back to what you squared before and just make the minuses pluses. And it'll work out that it'll end up as a plus 1/2 in the middle. And so it is the square of the same thing with the plus sign. Okay, it is 1 over 2 root x plus root x over 2, the whole thing square, and that's under a root. So they cancel out. That guy is a perfect square. And so when you take the root, you lose that, and you just get what's underneath. Okay, we need it to be a perfect square. Otherwise, we can't integrate it. Maybe we could do some clever U substitution in certain instances, but you know, this is what we have to do. And now that it is a perfect square, now we'll go and integrate it. We take the square root and the square, they cancel each other out. And now we go and integrate. This guy is x to the negative 1/2 over 2. And this is x to the 1/2 over 2. We add 1 to negative 1/2, we get 1/2. And so this would be 2 root x, but then it's divided by 2. See, we get x to the 1/2. And then I guess you can think about it as we divide by 1/2, but then this 2 is down here, so these guys cancel each other out, and we get x to the 1/2. Over here, we get x to the 3/2 by adding 1. Let's just say that we divide by 3/2, and there's this 2 down here, and these guys cancel. We end up with x to the 3/2 over 3. Okay, everybody okay with that? So that's how we get that term. And now we plug a 3 in, we plug a 0 in. Thankfully, plugging a 0 in gives us 0. So we'll focus on what you get when you plug a 3 in. When you plug a 3 in, we get 3 to the 1/2 and 1/3 of 3 to the 3/2. That's the upper limit. And the lower limit is 0. Okay. And the way this is going to work is you subtract the exponents. 3/2 minus 1 is 1/2. This guy, after simplifying, is 3 to the 1/2. And this is 3 to the 1/2. And you're adding them together. It's like the square root of 3 and the square root of 3, and you're adding them together. So you have 2 of them, and that's your answer. That's another way to look at it too. Anything to the 3s power is that guy times the root of that guy. Anyway, these guys cancel. You end up with 2 of these root 3s. So consider that the most difficult, when it's very hard to see that after squaring the derivative and adding 1, yes, we do have a perfect square. It's just a matter of recognizing it and be on the lookout for when you square something out and the only thing that changes after adding 1 is the sign on the middle term. Sorry. And the only thing that changes after adding 1 is the sign on the middle term, then it is the same square but with the different sign, with the plus sign in this case. Okay, and that would be it for our arclength lecture.